Okay, so let's pick up with example C in this video. And again, we're continuing to use the second derivative test to find relative extrema. Very different from using the second derivative analysis to find concavity and points of inflection. So try to know the big differences between a second derivative analysis and second derivative test. All right, so our four-step process for using the second derivative test begins with finding the places where the first derivative is equal to 0. So I'm going to take f of x equals x times ln of x, and I'm going to take the first derivative of that. And notice I've got a product of two functions of x. So in computing the derivative, we have to use the product rule. So the derivative is going to be the first times the derivative of the second plus the second times the derivative of the first. Now, we really don't care about when the derivative is undefined. The only thing that we're interested in, according to the second derivative test, is where the derivative is equal to 0. And this is kind of a special case with this second derivative test where we're only considering when the first derivative is equal to 0. But you can see the first derivative is 1 plus natural log of x, and we're trying to see when is this equal to 0. So this is a logarithmic equation. And to solve a logarithmic equation, we are going to write it in exponential form. And so you can see that your base is e. And so ln of x equals -1 is equivalent to x equals e to the -1, or x equals 1 over e. Okay, so now we're going to take our second derivative. Now our second derivative is actually kind of easy here because our first derivative was 1 plus ln of x. So our second derivative is just 1 over x. And step 3 in this process is to take the places where the first derivative was equal to 0 and to substitute that into the second derivative. And so we're going to do f double prime of 1 over e. And in the process, we end up getting 1 over our input. So 1 over e is just going to be e. And the important thing with that is e is greater than 0. And so what we just found is at a place where our first derivative is equal to 0, our second derivative is positive. And so that means we're concave up at a place where the derivative is equal to 0. And so x equals 1 over e is therefore a relative minimum. So you'd say x equals 1 over e is a relative minimum. And if you were asked in WebAssign to figure out what the y-coordinate was to that, we know that we can always get a y-coordinate for any x-coordinate by just substituting it back into the original function. So you would end up with 1 over e times the natural log of 1 over e. Okay, so that's example C. Let's go on to example D, and this is our last one with the second derivative test. So in example D, we again have another product, and so we have to go through the product rule. So first step of the second derivative test is to find the derivative. So if f of x is equal to x times e to the -x, then the first derivative is going to be the first times the derivative of the second. Now the derivative of e to the -x is e to the -x, but then multiplied by the derivative of the exponent. So it's actually negative e to the -x. So that's first times derivative of the second, and then we'll say plus the second times derivative of the first. And so this is equal to, that's x times negative e to the -x. So that's negative x e to the -x plus e to the -x. And we want to see when is this equal to 0. And so if that's one term and this is our second, I can pull out the greatest common factor of those two terms. And that greatest common factor would be e to the -x. And then we would also be left with negative x plus 1 is equal to 0. And so we would set each one of these equal to 0 and solve. But there's no solution to this part. And the reason there's no solution is if you took the natural log of both sides because you're trying to get the exponent down, on this side you'd end up doing the natural log of 0, and the natural log of 0 doesn't even exist. So you can't solve this. There's no x value that would ever make e raised to that power equal to 0. But here the solution is pretty simple. It's just going to be x equals 1. And so let's do a second derivative. Now, unfortunately, with our second derivative this time, we are going to do the product rule again. So you've got some options. You've got your first derivative. You can go back to this point. You're going to have to do the product rule on those two terms. Or you can treat your first derivative also as this right here. And I think I'm just going to work with the simplified version, but it's essentially the same thing. It really doesn't matter. You're just doing a derivative. Okay, so our second derivative is going to be the first times the derivative of the second. The derivative of this is going to be -1. And then we'll say plus the second. So plus -x plus 1 times the derivative of the first. And the derivative of e to the negative x is, again, it's -e to the negative x because we're doing chain rule. So we are going to see when is this equal to 0. And this time we've got, or no, I'm sorry, we don't need to see when this is equal to 0. What we should do though is we should simplify this. Because remember, we're not doing the second derivative analysis. We're just substituting the places where the first derivative is equal to 0 into the second derivative. So, so I might simplify this a little bit. And so we could say f double prime of x is equal to, I guess this would be -e to the negative x. Now notice you've got a -e to the negative x over here also. And so if you factored out a -e to the negative x, you'd be left with 1 plus, I guess that would be a -x plus 1. Or our second derivative is -e to the negative x times 2 minus x. Okay, so think about what x value we need to plug into this, and then based upon that we should be able to draw our conclusions. So the x value that we want to plug into this is x equals 1, because that's where our first derivative was equal to 0. So if I plug x equals 1 in here, it's going to give me a negative of e to a negative power. So negative e to the -1 is the same as negative of 1 over e to the first. You've got the calculator. If you want to use the calculator over here at the left, or the calculator that you've got in front of you, you can definitely do that. But I think that this is going to be a negative quantity, and then this is going to be a positive quantity because 2 minus 1 is 1. So f double prime of 1 is going to be negative. And what does that mean if at a place where your first derivative was equal to 0, you are concave down? So if you're concave down at a place where you had a horizontal tangent line, then x equals 1, I'm going to go back up top just because I ran out of room, x equals 1 is going to be a relative maximum. So x equals 1 is a relative max. And you know what, let's just plug this into the function and see if we can kind of confirm this. I haven't done this with some of the others, but this is really what you should be doing. You should do the work algebraically and always double check it graphically. So if I plug in x, and then we'll say e raised to the negative x, let's take a look at our graph. Okay, and at first glance it almost looks like this is not going to help us out and we might not be able to see anything, but all we really need to do, remember the behavior that we're interested in is around x equals 1, is zoom in on this a little bit. So let's see, if I press zoom in number 2, I'm just going to press enter. There you go. And you can even see, looking at this graph right now, you can see that that maximum is at x equals 1. We can confirm that by just saying second trace, maximum, that's number 4. Let's say a left bound of 0 and a right bound of 2. And let's just say guess, sure. Maximum x equals 1. So graphically it's confirming what we saw over here through the process called the second derivative test. Okay, so that's it for the second derivative test. And I will do one more video here where we just kind of go through some miscellaneous questions.